Okay, this circle looks even worse on the screen than it did when I drew it. I should have drawn the circle first. Always harder to draw a circle around a given point than it is draw a circle, then draw the point at the center. So no excuses. Have a look at the circle. It's supposed to be a circle. Okay, so we've got 10 microcoulombs at the center. That's actually a pretty big charge. And a 10 centimeter radius. What we want to do is sketch vectors that show the direction of the electric field and relative magnitude at every point around it. Well, to sketch those vectors, we don't need to do any calculations. Just sketch them, they're all radial. And they're all of the same length because, of course, magnitude, of course, is inverse square with distance, and they're all at the same distance. The forces would all be the same. So the force per unit charge is always the same. Now let's just do a quick calculation. The 10 microcoulomb charge have a 10 microcoulomb charge. I'm going to do this. On a charge Q. So assume there's some charge Q in each of these points. Okay, well, it's easy to calculate that. Okay. 10 microcoulombs would be 10 to the negative 6 coulombs. 10 centimeters is 0.1 meter. When you square that, you get 0.01 meter. So you have 10 to the negative 8 microcoulombs over centimeter over square meter. Okay. K is 9 times 10 to the 9th Newton meter squared per coulomb squared. So you have then 9 times 10 to the first. So this, whoa. I was getting that's what I was getting like 90. Yeah, that was ridiculous. 10 microcoulomb charge. Okay, so again, that's 10 to the negative 6, right? And this is 10 to the negative second in the denominator, which gives you 10 to the negative 4th. Multiplied by 9 times 10 to the 9th. Those are the numbers. The units work out to where this is. Nine times 10 to the 5th. Newtons per coulomb times Q. Now, assuming I did that right, you can do it yourself. Did a lot of it in my head. What's the electric field at that point? Okay, now, even after the homework, and I'm not being critical, I'm just telling you, it will be to your advantage because it's natural. When you first encounter something, not really have a very visceral understanding of it. However, the one thing you want to have a visceral understanding of is the relationship between force, field, and charge. But people came up with it, but not instantly. That means it tells me it's not a deep intuitive understanding at this point. So there's one thing you can do, make sure you understand how force, charge, and field are related. Because it's the first thing we did. First thing we did in class last time. It's only been 5 days. You have a big assignment. We missed Monday. But try to try to get the really fundamental concepts. In the electric field, in that relationship, are really simple concepts. We used it. Equals QE. And it popped up throughout the homework. Okay. So as you're doing these things, make sure you kind of focus on the simplest but most important relationships. Okay. So we see if the force is this times Q, well, force is Q times the electric field. This must be the electric field. 9 times 10 to the 5th newtons per coulomb. And what's that telling you? That's almost 1,000,000 newtons per coulomb. It's 900,000 newtons per coulomb. Almost 10 to the 6th. You have 1,000,000 newtons per coulomb, and you have a microcoulomb. How much force do you have? You have a Newton force. Okay. Think of what it means, newtons per coulomb, just like miles per hour. You multiply that by hours, you get your miles. Okay. Newtons per coulomb. You multiply that by the coulomb, you get your newtons. Okay, so you got your chart. I mean, your force here. So each of these could represent, depending on whether we want to make it a force or a field, could represent a force on it. The force, what it does, the way we've got it here, it does represent this force per unit charge. We never specify the charge. Okay. Well, generally it's a point charge. I kind of wish I could use the capital Q on that, is what I'm doing now, but a lot of times we use a capital Q for test charge. It's usually Q test or something like that. Okay. So we could be confusing notation a little bit here. But we get E equals force over your test charge, which I'll use a lowercase q test. The force is K times, well, it just with Coulomb's law gives you K times Q over R squared. Divided by Q test, which is just K times capital Q over R squared. I don't think it's a good idea to try to memorize this as a separate formula. It's more important to understand how it's related to Coulomb's law. So there's the development of this formula. So you should not only probably remember the formula, but it's easy to confuse formulas, which is why you really ought to understand where this one comes from. Okay, kind of work on that. Because it's a challenge to understand the connection between the reasons for formula and formula. Okay. Okay, well, now what I want to do is I want to talk about the flux of the field through a sphere. So this is a circle, but it's going to represent a sphere. And obviously, if you've got a spherical distribution with a charge at the center, the force on any test charge you want to put in that surface is going to be in the radial direction. Right? Which means it's going to be tangent to the circle or the sphere. Okay. Now we're going to be doing this in more generality. In monoverbal calculus. But an idea you really want to understand. Of course, in monoverbal calculus, we're going to prove that what I'm going to be telling you is really true. We're not going to prove that in physics. Because this is a course that's based on calculus 1 and calculus 2, not calculus 3, monoverbal calculus. You're going to understand where all this comes from. That time monoverbal calculus is done probably on about the last day. You'll understand it. I hope. Okay. Well, I'm kind of rambling, but let's go on with this. Okay, so what I want is the flux. Now, if you imagine we got this sphere, say it's a big sphere, okay? We got to point a really big sphere, okay, as big as this building, whatever. So we're at the surface of that sphere. And we take a little section of that sphere, and it's almost flat because it's a really big sphere, just like a line segment on the circle in a very tiny section of this circle is almost straight. And that should be a notion that's been reinforced through calculus and then everything else that you've been doing. Okay. So what we've got now is we've got this field coming out at a radial in this almost plane section of the sphere. If we multiply the field by the area of that thing, we get the flux. Okay. Now, if we do the field times the area on every little section of the sphere, and go ahead and shrink the sections down as small as you want to make it as flat as you want, then we're going to end up with just the field times the whole area of the sphere. Okay. So I'm going to just write a couple of statements here. He penetrates the sphere. At every point of the sphere. Okay. At a 90-degree angle to the local tangent plane. You want to ponder this a little bit. The flux through any incremental area of the sphere. And this needs proof, but it's intuitively not difficult to comprehend. Flux through any incremental area of the sphere. Let's say an incremental area delta S. That's actually a vector delta S. You take the area and multiply it by the normal vector, unit normal vector, and you get a vector. And you do dot products and all that stuff. We're not going to do that here. We're going to state more intuitive. If any incremental area delta S of the sphere is E delta S. if the angle wasn't 90 degrees, it wouldn't be E delta S. It would be E dot whatever the normal vector is at that point. For that small increment times delta S. Okay, we'll see what that means in a minute. Okay, going to use the letter phi sub E for the flux of the electric field. That's the sum over the entire sphere of E delta S. Now, you don't have the notation yet to write that out as it will be written out in monoverbal calculus, okay? So it's kind of intuitive, but just the delta S's form a partition of the sphere, of the surface. And their total area is the total area of the sphere. E is the same. I can say that the sum of your E delta S is E times the sum of your delta S's. It's E times the area of the sphere. So what would the total flux be for this sphere? Sphere of radius 10 centimeters, about a 10 microcoulomb charge at the center of the sphere. Now, again, it has to be at the center of the sphere. I'll turn out it doesn't, but right now, it has to be at the center of the sphere so that we can say E has the same magnitude everywhere, because it's at every point of the surface of the sphere, we're at the same distance from the center. And the charge is always, or the flux is always outward. And always perpendicular to the sphere. So all these conditions and more, I didn't write every possible condition I could have. All these conditions are fulfilled, okay? So that you can do this. So what's the total flux? Okay, well, it says your electric field times the area of your sphere, right? Okay, so okay, I think one of you might have used 9 times 10 to the 9th here instead of 9 times 10 to the 5th. That'd be real easy to do. So you kind of tune into that number. Okay, anyhow, we have this times. Well, the area of the sphere is 4 pi r squared. Okay. Something I'm not sure you can derive that from first year calculus. But we'll be deriving it. Yeah. Or too long and whatever. And you can derive it geometrically, but it's much easier with calculus. Okay, anyhow, it's 4 pi r squared. And 4 pi is about 12 and a half. And 12 and a half times 9 is about 1.1. So that's going to be approximately 1.1. Now 12.5 times 9 is like 100. 0.1 squared is like 100. So that's kind of a wash. I think I'm getting 1.1 times 10 to the 5th Newton meters squared per coulomb. Again, 4 pi times 9 is a something over 100. That's about a 10 to the second. And 0.1 squared is about 10 to the negative second. So I think we don't end up messing with that 10 to the 5th. Okay. Well, let's compare that with what it should be. Should be 4 pi k cubed. Okay, well, 10 microcoulombs is 10 to the negative 5th coulombs. Microcoulombs 10 to the negative 6, 10 ohms, 10 to the negative 5th. And multiplying this by 10 to the negative 5th, you're going to get a 9 times 10 to the 4th. I might have done something wrong with it. I'm getting like a 10 to the. Okay, well, let's see. 4 pi is about 12. 12 times 9 is about 100. So we're getting 10 to the 11th, and then times 10 to the negative 5th. I'm getting like 1.1. Ten to the 6th newtons per coulomb. I'm doing it in my head. That seems to agree with what we get here, but it needs to. So let me tell you why it needs some work. And then we'll figure out what the actual numbers are, and that's not difficult. Okay. So sphere, radius r. R to the center. The field equals AQ over R squared, doesn't it? In the area, it's 4 pi R squared. So electric field times area is KQ over R squared times 4 pi R squared, which is 4 pi KQ. Which means if these two are done accurately, they got to agree. So you can figure out which one it is. But right here's what's going on. And you didn't have all that on the screen. Okay. So again, the radius is R, charge is Q at the center. It follows that E is KQ over R squared, which we talked about right here. And the area of the sphere is 4 pi R squared. So when you multiply the two, you get 4 pi KQ. Okay, well, that's for a charge at the center of a sphere. Turns out, by the magical multivariable calculus and Gauss's law, and the most advanced thing we do in the whole course. Okay. The whole thing, most advanced thing we do in multivariable calculus is we prove that this works whether the charge is at the center or not, as long as it's within the sphere. And that's Gauss's law. Okay. So, Gauss's law, which is the divergence theorem. So that's a better circle because I'm not trying to put it around a given point. Okay. It works if you got a charge at the center. Total flux is 4 pi KQ. It could be anywhere within the sphere. So let's take it away from the center and put it here. Now the field is much stronger here. If this is halfway between the center and the surface of the sphere, field here is going to be 4 times as great. You're going to get a lot of flux through this part. You're not going to get as much flux through this part over here. Okay. And it turns out that that balances. And that puzzled for a long time. We're trying to figure that out with an actual interval. Back when I was taking physics and multivariable calculus, the electromagnetism. Never could get that to work. But I did understand the proofs of the divergence theorem, so I believed it did. Okay. Right now you just got to accept it. So Q anywhere within the sphere. Even if you randomly split this charge up and distribute it all over the sphere, or even if it's a cloud of charge with a charge density. Okay. It works. So Q is whatever charge is inside the sphere. Okay. Well, it gets even better. Doesn't even matter if it's a sphere. So you have any closed surface. Now, I think that may be restricted to orientable surfaces, but we don't know what that is yet. We do it in multivariable calculus. Okay. Any closed surface. You got total charge. This charge is distributed inside the surface. I don't know if you can read that. That's the idea. Well, right, there it is. Okay, so now we can figure out the field of an infinitely long charged wire. Or a long charged wire at a point that's not too close to the ends. It's an approximation in that case, but it's a very good approximation. Okay, so let's try to do that. Okay, so let's say we got it. Let's say it's a long charged wire. Now the charge has to be uniform. By simple, okay? If it's not uniform, then if it's a little more concentrated here than it is there, then the electrons that you got here are going to repel each other. And they're not, away from the region where they're more dense. And they're not going to be repelled as strongly from the region where they're less dense. Result being, they're going to have a net force toward the less dense region. And that's going to continue until they equalize. And we've talked about that to some extent already. So we've got a long charged wire. Density lambda. It's a linear density. Charge at a length L at lambda times L. Let's say that we want to get the field at this point. And this point is a distance A from the wire. Now, in the first place, and this goes with some of the intuitive stuff you would have done in the homework, it should be pretty clear that if this wire is really long or maybe even infinitely long, then for any increment you have over here, take an equal increment over here. And the field due to this increment will look like this, and the field due to this increment is going to look like this, and the net is just going to be in this direction. We talked about this last week. Are you familiar? So if it's a really long wire, or an infinitely long wire, you can do this for any increment. And you find that these increments always can be paired up so that your net field at this point has to be away from the wire, assuming that lambda is a positive density. If it's a negative density, then it'll be toward the wire. Okay. So this shows that the field is always raised because of this symmetry. And now what we're going to do is we're going to put a cylinder around this really around that, okay, we'll just do it from here we go. Let's do cylinder. Around any segment of this field. What's the direction? What, okay, what's? So this is length L. So what's the enclosed charge? What's the direction of the field? The increment of the curved surface. And same for the flat ends. Okay, so the answers we got to this question, if these are magnitude of the field, what's the expression of the total flux through the curved surface? Well, the answer I got is, well, it's like the sphere, it's like, the electric field times 4 pi r squared. Okay, well, no, because 4 pi r squared doesn't apply, but the idea was correct. And that it's flux times the area. But you got to have the area of the curved surface. What's the area of the curved surface of a cylinder? You cannot go through life not knowing this. Okay. And if it hasn't been demonstrated to you thoroughly, and the way geometry is not being taught, imagine it probably hasn't. Okay, right here's pretty good surface sphere. Cylinder. I wish I knew the names of these things. Okay, here's a pretty good cylinder. Okay. We can construct a flat surface, rectangle, in fact, that has the same area. Watch. That was pretty good construction, wasn't it? Okay, that was easy. In other words, we just think of slitting the cylinder parallel with its axis on one side and unfolding it. And its area is going to be circumference times its length. Circumference is 2 pi r. In this case, the radius is a, right? So, if these are magnitude of the field, what's the expression for the total flux in the curved surface? Well, it's E times A, which is E times circumference, which is 2 pi a, because a is the radius, times the length. If I slit this thing and unfold it, I get a rectangle of length L and radius 2 pi a. Make sure you kind of retain that as the. Okay. Now, what's the flux through this end? Okay, well, be really a pain to have to worry about the fact that the field gets stronger as you get closer to the water. Okay, and it does. We haven't really proved that though. But we have proved that the field is always perpendicular to the wire, which means the field is always going to be perpendicular to wire And the end is perpendicular to the wire, so the field is always parallel to the end. Okay. So the field's always parallel to the end, so it never penetrates. So we can say the field never penetrates the ends. But what's the flux through the end? Through an end. You show me some fingers. Okay, so yeah, field never penetrates the ends, so there's no flux through the end. So flux through the ends is zero. And I just asked about this end, but the same is obviously true for the other end. So we've got our total flux. That's one expression for our flux. We have another expression for the flux. Where do you see it on the board? Right there. Okay. So this equals this. So we can write some sort of emphasis. Here's one expression for the flux. I just rearranged it with the E on the end. Here's another expression for the flux. Well, we can solve that for E. Four pi KQ over 2 pi AL. But what's Q? Okay, so there we have it, but what's Q? Well, it didn't take long for somebody to. Then we charge from here to here. It's a length L for the charge with density lambda. So I've already written it out for you, but we understand what charge density means, linear charge density. This becomes then, well, first of all, 4 pi and the 2 pi divide out. For my A. 2K times lambda L divided by A times L. It's just plain old 2K lambda over L. Now 2K lambda over A. Okay. This means that it's inversely proportional to your distance from the charge. Make sure we don't exist. Okay, so it's well, it's an inverse first power. You have an inverse square here, you have an inverse first power here. Now, if you want to integrate the field from one point to another, you integrate the reciprocal R squared, you get a reciprocal R. So potential energy goes like the reciprocal of R. And we did that with gravitation. If instead of A, we now call this R, you know, because that'd be your distance from the axis, so something's a distance R from the axis. What do you get if you integrate 2K lambda over R? Well, you get a natural log of R. Okay. Natural log of R. What happens as R approaches infinity? The natural log of R. What's it approach? Well, natural log approaches infinity. 1 over R approaches 0. Okay. Means if you really had an infinite line of charge, you know, infinitely much potential energy. And so really can't say that, but that's one takeaway from all this. Still, if I've got a wire this long and take points, let's say between here and here that aren't too close to the ends, and points that are really close to the wire. Now there's points that are much closer to the wire than to the ends. We can do an integral and show that it might as well be infinite for all practical purposes. Okay. Or almost all practical purposes. And it depends on how much precision you need. So this is a good approximation to any line charge. So if I take, where is it? Okay, if I take this thing. Okay. And, you know, rub it across the cloth and break something. Okay, you know, I can charge it up. Probably best if I don't handle it with my hand. I can redistribute the charge that way, but this thing will become uniformly charged. Now it's pretty long, so we go all the way over here and all the way over here. Oh, there's the end. Okay, so the part that you see on the screen goes from about here to about here. If I want the field at a distance of 3 centimeters, you can easily calculate it. Okay. Or if I can observe the field at 3 centimeters, then I can calculate how much charge I put on the thing. Over later. Okay. Now there's another configuration we want to quickly talk about, and that's, let's say this whole surface is covered uniformly with charge. Well, then I could well, let's let this represent surface. Not going to stay as flat as I'd like. Then I can take a cylinder. Okay. I can't even see if this is showing up. Okay. Cylinders on this side, cylinders on this side. This cylinder encloses a charge that's equal to the area times the area density. Okay. If this thing is infinite, then by symmetry, the only direction the charge or the field can have is perpendicular to the surface. Now, it's not out of time. I can't really demonstrate that. But if I rotate the surface, that makes no difference in the infinite distribution of charge. Okay. And if I flip it, that makes no difference. So the charge comes straight out of this thing. So the charge through the ends of this thing, charge through the ends, I mean, the field through the ends it's the same on both sides. And it also doesn't depend on the length because it stays parallel forever. If it's an infinite. Charge distribution. The flux through the ends doesn't depend on how far you are. When you divide the flux through the ends by the area of the ends, you get the same thing no matter how long these things are. Now, for a finite charge distribution, that's still pretty much the case. As long as you don't get too far away or too close to the edges. Because everywhere except at the edges, if you're really close, the field has to be perpendicular. And you can feel that. Go to one of the screens we have set up in the halls. The warmth. Okay, now that warmth isn't an electric field, that's, but it's a radiant heat field that acts the same way. Close to the thing, close to that screen, if you're this far away or this far away, close to the center of the screen, you're going to feel about the same radiant energy. Okay, same radiant power. It doesn't fall off until you get a ways. It doesn't fall off significant until you get a ways from it. And if you really kind of do that, you put your hand close and pull your hand back a little further, it's going to feel about the same. Okay, total analogy to this. Because it's straight away from the surface, as long as you're much closer to the surface than you are to the edge, same idea. And you can read about it, and you need to read about it. But what happens then is the field of this thing is always the same no matter how far you are from it. If you have two of these very close together, my paper's mixed up. If you have two of these close together, and you pull charge off of this one and deposit it on this one, you get equal charge distributions. And in between those, the field doesn't change much. So you can figure out how much energy it takes to get from one to the other. That's capacity. Okay. So we'll talk more about that. These are important distributions. Okay, you can have spherical capacitors, you can have cylindrical capacitors, you can have flat capacitors. And to understand those, you need to understand Gauss's law. So read on it, get working. I don't need to talk about this on